We've certainly seen this circuit before. This will now be the third time that we examine it, and you might wonder what there is left to do. Remember, the first time we analyzed this circuit by applying boundary conditions, and we came up with 4 equations and 4 unknowns, the 4 unknowns being the wave amplitudes on the 2 transmission lines. And once we were able to solve for those wave amplitudes, we were able to determine the value IL and VL. The second time we went through, we used the accordion, the equivalent circuit technique, where because we had special cases, we could quickly replace everything over here with an equivalent circuit, analyze the simple source with 2 impedances in series to get the voltage and current here, and then propagated that voltage and current from here to the end of this transmission line, and from here to the beginning of this transmission line, and from here down to the end of the transmission line, where we could go through and determine IL and VL. Now, the propagation occurred by going through and solving 2 equations and 2 unknowns to find the 2 unknown wave amplitudes. Once we knew the 2 unknown wave amplitudes, we could determine the current and voltage at this end. KVL and KCL gave us the current and voltage at this end. Then we had to stop and calculate the 2 unknown wave amplitudes on this transmission line, and once we had V0 plus and V0 minus, then we could determine the current and voltage everywhere, including the end of the line, where we went through and found eventually VL and IL with KCL and KVL. So we're going to do the same process again, the same equivalent circuit, crush it up and then expand it back and propagate the answers back. This time, however, instead of taking voltage and current at one of the line, finding the unknown wave amplitudes V0 plus and V0 minus, and then recalculating the current and voltage at the other end, we're going to use our transmission line identities. If you notice, each of these transmission lines are a quarter wavelength, and so we'll find once we determine the current and voltage here at the end of the line, we can use our identities to directly determine the current and voltage at the other end of the line, a quarter wavelength away, without ever having to determine specifically the complex wave amplitudes. We can very quickly propagate an answer from one end of the line to the other end of the line to this line, and then down to the end again, without having to stop and again solve 2 equations, 2 unknowns. We immediately apply our identities, and we'll find it's a much quicker way of being able to get to the answers, and we can apply those identities when we have transmission lines that are a quarter wavelength in length, as these are. So the first step is precisely the same as we did in the last analysis of this circuit, where we applied equivalent circuit. We used the quarter wavelength transformer to determine the equivalent input impedance. Again, this is incorrect. It's 800 ohms is the correct answer, not 12.5 for the input impedance here. But now we have a simple circuit where we apply voltage division and Ohm's law rather, to determine this voltage V out and this current I out. Now, by KCL and KVL, we know this voltage V out is equal to the voltage here at the beginning of the transmission line, and the I out is equal to the current at the beginning of the transmission line at a value of where we evaluate the index of the total voltage and total current. And so from that, once we know the voltage and current at the end of one transmission line of a quarter wavelength, lambda over 4, we can use our identities to immediately determine the current and voltage at the other end. So this is going to be an identity that we use. Identities of this type is going to come in very handy. So this is how we would apply this identity. We know at this location on the transmission line what the current is, what our total current is at this location. It's J.02 amps. If we move down the index a quarter wavelength, and in this case we're moving in the direction of increasing z, so we start here at minus lambda over 4, that's our index. We add lambda over 4 to it, we're increasing z, and of course we add lambda over 4 to minus lambda over 4, we get an index of z is equal to 0. So we're starting at a point and we're adding lambda over 4 to get our new point. And so we can take the current at the original point and find the voltage at this new point a quarter wavelength further down the transmission line. So make sure you see that and use the right identity there. When we do that, so we take our original point and we find the current now is again j 0.02, and we multiply it by minus j times the characteristic impedance of this transmission line, which is 100, and that gives us a value of 2, a complex value of 2, imaginary part of 0 and a real part of 2, and that is then the voltage at a point on the transmission line that is 1/4 wavelength further down the line from the original point. And of course that point then is at the other end of our quarter wave transmission line. We start at the current at one end and we can determine the voltage at the other immediately without having to resort to calculate the complex wave amplitudes V0 plus or V0 minus. Just immediately put our current value into this equation and out pops the voltage at the other end of the transmission line. Now, to determine the current at the other end of the transmission line, we can use this identity. So we start with the voltage at some point on the line, and we can determine the current at a point which is a quarter wavelength further down the line, the direction of increasing z. So if we take the voltage here at this location, and we know that voltage to be J16, and we got that from our voltage division we did on our equivalent circuit, and then we move down the line a quarter wavelength. Again, we're starting an index minus lambda over 4. We add a lambda over 4 to that, and we get a value for our index then which is equal to 0. Again, we increased the index z by a quarter wavelength, and that's what we're doing here as we move down the line. And so we take our original voltage at the beginning of the line, all right, which would be this here, and then we divide by Z0 and multiply by minus J, and the result we get is 0.16 amps, a complex value, a magnitude of 0.16 and a phase of 0. And that is the current then at the other end of our transmission line, a distance of lambda over 4 from the original point where we knew the voltage. The voltage here got transformed into the current at the other end of the transmission line. So what we did, again in summary, is we took this current on one end, and from that we could determine the voltage on the other. And we took the voltage at this end, and we determined the current on the other. And we could do this because this transmission line is 1/4 wavelength in length. So I'm combining some steps here, but hopefully, again, we've done this before on the other analysis of the same circuit. If I know the current and voltage at this end of the first transmission line by KCL, I know that current likewise must be the value of the current at this point on the second transmission line. And the voltage, if I know the voltage at the end of this transmission line is 2 volts, then the voltage here at the beginning of the next transmission line must be 2 volts as well by KVL. Well, if I know the current at the beginning of this line, and I know the voltage at the beginning of this line, and this transmission line is lambda over 4 in length, and it is, I can take then this current, for example, and transform it into a voltage using this identity. This point, again, is a quarter wavelength further down the line, and so we use this identity. The original current, which is right here, of 0.6, multiply it by minus j times the characteristic impedance of 25, and that'll give a value of minus J4, which is equal to the voltage 1/4 wavelength further down the line here at the other end. We've taken the current at the beginning and determined directly the voltage at the end. And similarly now we take the voltage at this end of the line, and because it's quarter wavelength, we can use this identity to determine the current at the other end. We take this voltage of 2 volts and we insert it in this identity, and we get a current at a quarter wavelength further down the line right here, and that value is minus J 0.08 amps. 2 transforms into this current by using this identity. So once again, this current led to this voltage, and this voltage led to this current. We could instantaneously almost determine these values simply by using these identities. And so then once we know the voltage and current at the end of that last line, we know by KVL that the load voltage must be also equal to minus J4, and the load current must be also equal to minus J 0.08. So we get our solution. And of course, these are precisely the same solutions as we earlier derived, both using boundary condition and our accordion or equivalent circuit analysis. And again, this was the equivalent of circuit analysis we just did. The only thing differently was that we applied identities, which allowed us to propagate the answers along our circuit from one end to the other in a much more timely manner. We didn't have to stop and determine, take two equations and two unknowns to determine the unknown values of our complex wave amplitudes V0 plus and V0 minus. No simultaneous equations. And so you can click through the analysis pretty quickly to get the answer for the currents and voltages at either end of either transmission line. So that identifies the potential drawback with this technique. What if you want something other than the total current and total voltage at either end of the transmission lines? Let's say you want the total voltage or total current halfway down the line or a third of the way down the line, some other location other than one end or the other. Let's say if you want to know some value of the reflection coefficient function as opposed to total voltage or total current, or the minus wave voltage or plus wave voltage at one location. What do? Well, we still know that if we go back and determine the complex wave amplitudes V0 plus and V0 minus for a given transmission line, then we can determine anything we want. Current, voltage, reflection coefficient, line impedance at any and all points on the line. So once we find those, we can determine what other value that you need. And so if you do need something else, then you can stop and use the knowledge that you have for voltage and current at any point on the line and solve for the unknown wave amplitude. So again, if you know the voltage and current at one end of the line or the other end of the line, you can use those to directly determine those unknown wave amplitudes. If there's a point on the index called z is equal to 0, that's a useful place to apply your simultaneous equations because the mathematics are a little bit simpler in terms of the analysis. So again, if what you're interested in is a voltage or current at the end of one end of the line or the other, these identities are make the analysis of the circuit much simpler and much quicker to get the correct answer.